Alright, so now let's take a function f of x comma y comma z. Okay, so this function has three input variables. And integrate f over the box. The following box B, so B will be defined as a set of all points in three-dimensional space, so every point of the form x comma y comma z satisfying the following conditions. So x is between a and b, and y is between c and d. And to avoid using e, I guess the book uses r and s here. Okay, so picture. Now there's a picture of the input space only. We can't draw the three input dimensions and the output dimension w as well. That would be a four-dimensional picture. So within the input space here, so within x-axis, y-axis, z-axis, right, somewhere within here, there's going to be a box somewhere. It doesn't have to be down at the bottom necessarily, but somewhere there's going to be a box. So this is a little challenging to draw, but you know, somewhere like maybe over here, there's a box on the bottom that looks like this, and yeah, just roughly speaking, you know, it looks something like that, right? So we're going to integrate over this shape. Right, so this is an example of B. As chosen, this box is kind of small, but it could be big, right? Just depends on how far apart A and B are from each other and so on. So what we do is, a little bit as expected, similarly to other definite integrals, we make Riemann sums by cutting this solid box B into tiny rectangular prisms. So think about something like a Rubik's Cube, right? So Rubik's Cube is only cut into three slices in each direction, but if you were to cut more. And what this ends up leading to is a little bit of volume is really the product of a little bit in the x direction, a little bit in the y direction, and a little bit in the z direction. So you pick a point. Next you pick a point, which would be like an x I j k star, y I j k star, and z I j k star in each tiny little rectangular prism. In each tiny rectangular prism. If you want for a little more clarity, in the sort of I j kth rectangular prism. And this is going to give, I don't want to call it height really because it's in the fourth dimension, but whatever that would be, you know, in the fourth dimension, when you apply the function f to this input x I j k star, y I j k star, z I j k star, that's going to create a w coordinate which will end up representing the fourth dimension of this four-dimensional rectangle. So then the volume, I put the word volume in quotes because it's really a four-dimensional volume. So think about how in two dimensions you have what would be called area, in three you have volume. In this fourth dimension, what would that be called? Well, that's what we're talking about here. Okay, of one of these four-dimensional Riemann fries, you know, back to the French fry analogy here. This is going to be take the height height in quotes, take this number, the w value, ijk star z sub ijk star. Okay, take that height, and then you multiply by the change in x, change in y, and change in z, all summarized by change in v. So then, what we have is the triple integral of f, the function f, over the solid box b would be the following. So the triple integral over b of f of x comma y comma z dv. This is under the hood, it is actually evaluated as a limit as L approaches infinity, a limit as m approaches infinity, a limit as n approaches infinity of the sum I going from 1 to L, sum j going from 1 through m, sum k going from 1 through n of f of x sub ijk star, y sub ijk star, z sub ijk star, delta v. And so this part right there was just the volume of the little box, right? Volume of little box. So within this here, there's like a little box here that we're finding the volume of. And then this part here then, right? So that's the four-dimensional volume, right? Of one four-dimensional fry, right? So this is the volume of one four-dimensional fry, and I'll put volume here in quotes because it's this four-dimensional concept of volume. Okay, then if you go this far without including the limit, then you have, this is the Riemann sum, but then when you include the limit, so the Riemann sum is just an approximation, right? This is an approximation as before. And then the limit, if it exists, is the exact total volume in quotes again. Yeah, so this is an approximation of the total volume. And yeah, the limit, if it exists, is the exact volume in quotes, right? Because it's four-dimensional. Under, in quotes, under in sort of the w direction, the graph of w is equal to f of x comma y comma z. A couple other notes. This dv right here, we saw delta v up here, so maybe not too surprising that dv, at least one of the ways to write it would be dx dy dz, like this. Okay. What ends up happening through a version of Fubini's theorem is so this might be technically how it should be computed, but we don't have time to always set up a Riemann sum and take limits and so on. So more practically, the way this gets computed is the integral from r to s, integral from c to d, integral from a to b of f of x comma y comma z, and then dx dy dz. At least that's one order. There's other possible ways to do this.